about the system before we are going to go through the lecture slides. So today lecture title is what we call it the pneumatic conveying. It's written here. I'm going to show you some example. If you just search on Google about the pneumatic conveying, you'll find something like those photos. Actually, you can write down here. You can find something like these photos. Or if I'm going to go to the actual things, like for example, looking for videos, that you'll find many resources tell us what is the pneumatic conveying system is. Now, from the name, conveying, that means we need to remove a material. This material is bulk material. Now, once again, it's not unit load. We're again not going to move boxes using the pneumatic conveying, though that actually in some of the old application for it, we can move capsules. Well, actually small capsules like this size, for example, the size of the fruity bowl, using the tube, pressurized tube, so we can push it from one place to another. It was very common method back in the 50s, 60s, and 70s to move the letters between the different departments at the Pentagon in the United States. And also, I think it was used in many hospitals to move the medicine between the different departments in very high speed and safe format. So I think well, this video looks nice because talking about the coffee. I'm going to click on this one, and the problem I have is I cannot share the voice with you guys because I have a filter. It's an ad. Okay. Now we can see that it's going to give us brief about the pneumatic system. Pneumatic system. So it's just simple way to move the material from the side number 1 to the side number 2. It's usually going to be used with the food material because we would like to keep it clean. And also the most important thing, we would like to keep it unbreakable because we don't want to buy a coffee that to re-grind it. We want to have it as a full drink. So other video we can see here, again to share this one with you of course later, is about how to move the plastic pellets from one side of the factory to another, doing some of the pre-mixing processes for the pellets. So these are some of the example video we're going to see later, because it's very important actually to know what would be the type of the pneumatic conveying system. For example, we have the dilute phase, we have the weight conveying, and we have the Dennis phase. Different methods, and each one is going to have a different application. What are the use are mentioned in this example. You can see that, well, you can simply have 2 different silos. We're going to fill them with the, for example, wheat or whatever the grade is, and then we're going to pump it using the air to the top and fill the storage silo. Way to do that, we can do it either by pressurize the air, okay, as what we have in what we call the positive conveying. That's what we can see on this side, or we can have it as a vacuum conveying. Well, for the vacuum conveying, the silo itself is going to work exactly as a vacuum cleaner. It's going to have negative pressure inside, and thus we're going to have negative pressure all over the pipe, and thus it's going to pull the material and dump it inside the silo. In both cases, we're going to need a vent filters, because in this case, we're going to have positive pressure in the pipes. We're going to pressurize the tank, and we need to have a vent for it, so we're going to keep the balanced pressure. And the other one, we're going to do the blower. Once again, just like the vacuum cleaner, we're going to need the filter to separate the air from the material. This will be another material to be shared with you soon. Multiple examples about the equipment we need for the pneumatic conveyor. For example, we have that device which is called the feeder. And this feeder is going to submit the material into the conveying system as patches. I'm going to show you how it's worked. The blade we have inside look like a star. If you're going to cut it from the side, it's going to look like a star. Have long length along the square outlet for the hopper, and start to submit the material patches by patches, which is going to run through the pipe to the silo. This is another example for the process. This one is for the vacuum conveying. So you can see in the vacuum conveying, we're not going to have the pump here like the case of the pressurized one. In the case of the pressurized type, we're going to have the pump standing here, air pump, blow the air inside, and the material will flow directly from the hooper, running through the pipe and fill the silo. Now, if we're not going to have the feeder, if we are going to have the hooper going to be directly connected to the pipe, we are going to have what we call the Dennis phase. In the Dennis phase, the hooper will be pressurized, and thus the flow of the material is going to be continuous instead of patches like what we have in the case of the blower or the lean phase conveying. Once again, we're going to see video for everything we're talking about. This is just an introduction of everything. Actually, back in the old days, when I say old days, well, till 2019, we used to go to University of Wollongong during all the lab sessions there, including the 2 lab sessions we did at the UTS. That's before I discovered that the civil engineering people have the same equipment, at least for the shear test and for the sieve test. We used to go to Wollongong University, and they have something similar to that lab. Maybe this one a little bit larger, but they used to have something similar to this one. And we were taking some data and started to do our lab calculation. Again, this will be, actually this journal processing is giving you most of the state of the art of technology we have for the bulk material handling. More example we have here about the pneumatic conveyors. This actually tells you about the type, the design, and the uses, and this will help you a lot if you are going to apply for a job related to the to that thing. You can see that the pneumatic system actually is going to be used not only to convey the material, though it's being called the conveying material, but also it's going to be conveying the material within the processing application. For example, you can see this one is stainless steel, conveying the air, and then it's going to be supplied to a certain application. Very common method in the food industry and also in the pharmaceutical industry, because once again, we want to keep the material as clean as possible. So every contact with the belts or the screw conveyor or whatever the thing is, we're going to have a contact between the material and metal. But if I get to push it with the air, it's just air. It's only going to have contact with the air, pure air, filterized, and then we're going to keep the material as clean as possible. Also, some of the material that cannot be carried by the open environment, like what you can see here, the wheat, the sugar, the cement powder, the sand and other aggregates, and also, let's say, the ash and the flour is also can be carried by this operation. Different types, as we mentioned earlier, it can be negative and it can be positive. This one is positive diluted phase pneumatic conveyor. We're always going to know it's diluted because we are going to submit the material as patches. When this plate is going to rotate, each time it's going to give a patch into the pipe one by one, and then we're going to have the material to be sent in a small quantity within larger amount of air. For the dense phase, we're going to supply the material continuously through the pipe. So as you can see, continuous flow of the material to be happening inside the pipe. Okay, so you can see that in that case, the whole tank is going to be pressurized, and thus we're going to force the material to run through the pipes. Some of the specification and selection criteria are given here. Look at the distance, the flow rate, and the pipe design. types of the filters, the fan vents, and the protection we have. The control and special construction for this system is also being mentioned in this page. And other things to be shared with you. I think the last one is going to be, once again, just definition of the technology, very small one, and does have some of the application that will give you more idea about what we have here. I will leave some of the videos I had here until we are going to actually have the technology being explained to you within the lecture slide. Okay, so most of the design processing we have for this technology is going to depend on the fluid dynamics. So if you know the principle of fluid dynamics, you will understand the concepts of the pneumatic material handling. And as I told you that because this subject is just give you the first step in the correct direction, I'm going to give you a brief about this technology, and the rest is going to be your responsibility to look after. I will give you one example, and then I'm going to give you a second example, a question, which is going to be a part of the assignment number 4. Now, I know that the assignments are accumulating very fast, but you don't have to worry about that. The main concern we have is we are going to lose something about 2 weeks in a row after the student break. So we need to arrange a time, especially to finishing the assignments which are coming after the closing date of the next assignments, or of the recent assignments. For example, we are going to have the due date for the assignment number 1 is going to be Friday. On Friday, I'm going to release assignment number 3, and next week we're going to have a tutorial for this assignment. The week after, we're going to have the lab session, the lab report to be due, and after that, we're going to release the assignment number 4. The assignment number 4 is covering today's lecture, and next week's lecture was going to be the hydraulic conveying. The assignment number 4 is divided into 2 halves. One of them is going to be something like a quiz. I don't have to actually observe you doing the quiz. I'm going to open a window for this quiz for, let's say, 90 minutes. You are going to get the question, start to do the solution, then scan and submit. All should be done within 90 minutes. We need to have a pool on that, what will be the most suitable day to run this quiz. It's only going to be the window is going to be run at the same time for all the students, and we cannot make an exception for anyone. The second part of it is going to be calculation part, and is going to depend on the level we're going to cover today. So let's go about pneumatic conveying. For the name, well, I just mentioned that the main aim of the lecture is to provide the general overview. So I'm going to be a deep overview of the pneumatic conveying, and the objective is going to talk about the typical materials we are going to have using pneumatic conveying, the basic components and the systems, the modes of the pneumatic conveying characteristics, and also the important equations for the PC, which is the pneumatic conveying system. I think that most of you saw something similar to this, I will call it tank, but actually it's silo. Have you seen this thing before? Have you seen this tank before? Well, this one is made of stainless steel, as you can see here. This one is silo, and this silo is used to transfer either the, for example, dry milk, powder milk, the fluid, or the, for example, any type of the food grade material. You can see the white one, but doesn't have to be too clean, which is used to transfer the powder cement, for example. The most important thing in this system is that unlike any type of the silo, it's having these pipes below there. We have pipes, we have the tubes here, and it should be sealed from the top. Now, this kind of silo is actually a pressure vessel. Have multiple hoopers there. We fill with the powder. When we try to fill it, just open the cove at the top, fill it, and that's it. Now, if I would try to empty it, what we are going to do is, can you see this pressure tube here? Now, we're going to connect it to a high pressure compressor, and the whole vessel is going to be high pressurized. Then we're going to open the outlet here, and the material will start to follow in this direction and go to the silo. As simple as that. So this is one of the most common pneumatic conveying system we have in our life. So that's what will happen. Actually, is the pressurized air is going the compressed air is going to pressurize the vessel, and the material will start to flow from one side to another. That's another example for the pneumatic conveying system. And in that case, we are going to use the dilute phase or the batch phase to do a mixing for the materials. So you can see that we have here 3 hoopers, and we have the feeders. So by controlling the speed of the feeder that feed the pneumatic pipe with the material, you can see that we can have a different combination for the mixing of 3 different materials. They're not moving the same. For example, I need to have 2 volumes of the blue, 1.5 volume of the gray, and 1 volume of the red. So I can control that while the material is going to be accumulated in the mixing tank, and then it's going to be mixed. This will be one of the best methods we can do, because we're going to have the pre-mixing, then we're going to have the final mixing within the vessel. So pneumatic conveying in general, as a definition, is a method of transporting the bulk materials in the form of the powder or short fibers and the granules over the pipeline as a mixture with the air or due to the pressure of the air. The pneumatic conveyor system using the differential air pressure. We're always going to have different pressure between the inlet and the outlet. This can be positive and it can be negative, and this will efficiently move the materials from one point to another. Since the airflow from the high to low pressure is the application is going to be at one end of the pipe will move the bulk material to the other end of the pipe. These systems are going to be classified as a negative pressure if they're going to do the sucking process, or we can have, or we can have the positive pressure device that compress the air to push the bulk material. So once again, negative pressure is going to pull the material to the tank. The positive pressure is going to be pushing the material to the tank. Okay, so on application of the pressure of the vacuum, the solid particle will become airborne, and thus they are going to be transported along the pipes. The different materials are having the different shape, of course, sizes, weight, and physical and chemical properties. Therefore, we're going to have different machine designs are going to be required for various conveying systems. So we're not going to have a universal type of the machine for all the materials, because some of them, if we're going to use it for bigger size of the material, we'll start to break it up to small particles. Usually the patch type, which is going to use the feeders, we try to avoid using it with the powder format. We can use it for the granule shaped particles. So this will be done by varying the pressure, the quantity, and the velocity of the airstream inside the pipes. These are some of the typical materials which are conveyed pneumatically. So you can see is most of these materials we can have here is going to be either a small size granules or it's going to be a powder. Usually we try to avoid using that with long shaped particles. So you can see the kaolin is going to be a powder, the lead oxide is powder, lime can be crushed or can be hydrated, but usually you can see that this should be sub to 50 millimeter maximum diameters. Anyway, it's light material. The maize, the manganese dioxide, the milk powder, we have the cobalt ore, the coffee beans, the coke, we have the corn and corn grits, the raw meals, and so on. So it's a long list actually of the material that can be conveyed, and you can see that most of these materials are going to be conveyed in a processing facility. It's not just to convey it in a long system. I think, yeah, the sulfur is mentioned here because usually the pneumatic system need to be either a short distance transporting methods, or we need to make something like substations that keep increasing the pressure continuously, or maybe we're going to pump it between stations, like from silo 1 to silo 2, the distance is not going to be more, let's say, than 100 meters. It's going to be a small size. And we can connect it to take it to a long distance. I remember back in the 90s, there was a project to transport the sulfur from the silver mines somewhere in the desert in Iraq to another city, but actually it didn't work because they couldn't provide the large pneumatic pumps at that time. So the basic components we have for the pneumatic conveying are very simple. What we need are going to be first, we start with the prime movers, which can be either the fans or the blowers. The compressors can be divided into the respirating types or the rotary screw. And we're going to see that actually it doesn't much different from the compressor you're using in other applications. Now, the second step after we pressurize the or move the air, we need to add the material, and this can be done by using the feeding, or the mixing, or the accelerations. We can do that by using the venturi, which is going to send the air from one side, and the material is going to be fed from the other side, and we're going to have mixture, which is going to be accelerated, very high speed, and moving to the end destination. And we have the rotary valve, which is going to, once again, feed the material in batches. And we have the screw conveyor. It can feed the material continuously and preventing the air pressure to go backward. And we have the blow tank, which is going to be pressurized. Now, why we need to have these equipment? Otherwise, the pipe is going to be pressurized. It's going to push the material up unless we're going to use some of the feeding equipment. So in that case, the velocity here is going to be much higher than the velocity of the air at that point because of the venturi effects, and thus we are going to prevent the air to blow up the material upward. Instead of that, they are going to be mixed and going through the outlet. For the rotary valve, the air is going actually toward that. It's not going to be coming from this way. It's going to go inward in this direction. So it's going to take the air is going to take the material through the plates patch by patch, and no air is possible to go upward in this direction. For the screw, the same thing. The material will be fed in this direction. It's very rare to have the effects of the pressure to push the material backward. And of course, for the blow tank, we're going to have higher pressure inside the tank, and this will prevent the air to blow the material upward. Now we mix the air with the material. We're going to send it through a conveying, and this should be either pipes with vents. We are going to have some derivatives in the way to do some mixing, for example. And we need to join the pipes, the vents, and the derivatives using the coupling or flange. We always have a wear resistance materials. Now, why we should have a wear resistance material? what's happened? Why we need to have a wear resistant materials to be used for conveying? Actually, the answer is going to be very simple.
There's too much friction when it's moving.
Exactly. So the material, we're transporting is going to grinding the wall a lot. So we need to have a material that for the wall or the pipes should be a high resistance to these frictions, and thus it's not going to be very easy. And actually, I'm going to show you one of the main problems we have in the conveying system, which mainly caused by the friction. And as we are going to reach the end of the system, we need to separate the air from the conveying material. Usually what we need is what we call the separation device. One of the most common separation devices are what we call the cyclone. Also, we can use the back filters like the mechanical reverse jets. So once again, just simply as the vacuum cleaner. Again, to have the bag, it's going to allow the air to go through, but not the dust, which in this case is going to be a mixture of the air and the powder, for example. So it's going to hold the powder, not the air itself. The separation time is going to depend on what we're using. Are we using the gas or using a solid material for holding the Now, the first type of the air movers is going to be the centrifugal blowers. Usually, this will be used for the positive displacement. So, this is a type of the positive displacement. That's my centrifugal blower. It's going to take the air from this intake and send it out due to the movement, the high movement of the plate, and send it as a high velocity pressure through the pipe. Now, here we are going to have the mixing point. This will be a feeder. Feeder is rotated by this motor, sending the material inside the pipe, and it's going to be mixed with the air coming from this bending up and send the material through the piping system. Now, this will be another example of a centrifugal fan. Okay, so actually this centrifugal pump, which always going to be the same concept. This will be centrifugal fan, again, to have the air coming from this direction and the air getting out from this direction. And later it's going to be mixed with the bulk material and start to move it. Now, another type of the movers are going to be the roots type blowers. So these are very complicated and very high sensitive equipment. And actually, you can see that we are going to have two gears inside, and they're going to have very high tolerances between them. So when they're going to move at very high speed, they're going to generate higher pressure. Now, you can see what the size of this type, and actually this will only going to make the air pressure. It's not going to be for liquids. But the size also can be as small as this one. Okay, we can move the drive, and the follower will be following. For example, here we're going to have a pulley. We're going to have it on the other side, connected with the belt to the motor. As the motor is going to rotate, we're going to have pressure to be generated, and it's going to be fed to the system through the outlet here. So the roost type flows, as you can see here, we can have it the two plates, we can have it as 3 plates. The flow is going to be very easy, as these 2 plates are going to be moving. We're going to have negative pressure on that side and positive pressure on the other side. Different arrangement, but the concept is always going to be the same. This is the same photo we had earlier. And we said once again, we are going to have some jointers between the piping and the blowers. You can see here that we're using the flexible joint because this will prevent the vibration coming from the roots type blower to be transferred into the conveying system. Because you know the vibration is always going to have negative effect. We can also have the screw compressor. Now, the screw compressor is one of the most common design. We have it in many applications. Like, for example, we have it in the air conditioning. We have it on the top of the chiller, or we can have it as a compressor for the freon, and so on. In the screw conveyor, the shape of the plate is going to be a screw shape. And thus, the contact area is going to be quite longer. At high velocity, the pressure difference between the input and the output is going to be very high. Now, the most important thing that this device should be oil-free, because we don't want to have any contamination to contaminate with the material we are transporting. So different types of the screw conveyors and also the other types of compressor plates we have in our pneumatic output. Now, the feeders are another device that how to feed the material to the pipe. So if I get to have the pipe just running below, and I try to feed the material from the top, the pipe pressure will push the material up. So we're going to see a fountain instead of having the materials to be mixed with the air. So we need the feeders to make the mixing possible. One of the most common feeders is what we call the rotary valve. The rotary valve, once again, we're going to have the axis of rotation is horizontal, and the plate is going to be running horizontally. We're feeding the material. Each compartment in the plate is going to be fed individually, and when it's going to be in the same direction of the flow of the air below, it's going to submit the material to the air stream, and then the material will start to run through the pipes. So that's how the feeder is working. Okay, this is the axis of rotation. We fill the different compartments, and we're going to submit the material by patches into the feeders. Now, the speed of the feeders, like the rotary valve, is going to decide what will be the percentage of the material in the mixture. Okay, and thus is going to decide, of course, what type of the flow we're going to have for the mixture. Another example for the rotary valve is what we can see here. Now, this type have two rotary valves together. Now, the concept is going to be the same. The most important thing for us is we try to prevent that the air from the blower to push the material up in the hooper. Instead of that, it's always going to be in one direction. Now, why we have the two rotary valves here? Because this will simply going to send the material in a patch, which is going to be filled here. Now, the feedback from the shop air is going to pressurize the material further down, and then we're going to prevent any possibility for the air to pass it through the walls and push the material backward. The two main types we have for the rotary valve are going to be either the draw through or the blow through. Draw through or the blow through. Now, these are the difference between the two types. You can see that the main difference is going to be because of the shape of the plate we have. This one is going to be straight, and this one is going to be inclined. So the concept is always going to be the same, feeding the material from the top. This side is going to be connected to the hooper, and start to feed the material as a line, okay, and feed it to the outlet. The other type is going to prevent the air from coming up from the side of the walls, because this side is not going to be in the stream way unless it's going to pass further distance. So thus we are going to prevent any possibility for the material to be pushed up and having flow back. Okay, so actually in the future, if you can see, actually it's very hard actually to know that by taking a look from the on the valve from the outside, but well, I just choose this photo in general. But you can see that, okay, now for this one, you can see that the plate is rotating in this direction, and the material is going to be fed on the opposite direction, because we are going small vessel at the bottom. Now, for this case, the plates are going to be running in parallel to the air stream direction, and thus we're going to have the blow through to take in the material and push it through the system. Now, one of the rotary valve issues we have is going to be the feed rate value, or the MS. We're going to take this equation now and we're going to apply it later in our calculation process. So the feed rate of the rotary valve in kilogram per minute is going to be equal to the alpha, which is the material filling factor, because you know that the cavity or the compartment not going to be filled by 100%. So we have the alpha value, which is material filling factor, multiplied by the bulk density of the material, multiplied by the soot volume in the cubic meter per revolution, how much material is going to be running, multiplied by the N. Now, more material filling factor is going to increase the feed rate. More higher density is going to increase the feed rate. A more soot volume for the compartment is going to increase the feed rate. And finally, if I go to simply increasing the RPM value for the rotary valve, it's going to increase the feed rate to the system. So each one of these factors is going to decide what will be the feed rate volume we're going to have for the material. Now, the main problem we have is going to be the air leakage through the system, or the QL. So the QT is the value for the total volumetric flow rate of the air from the air mover or from the pump. The QL is the amount of the air that's running through the rotary valve and pushing the material backward. And this is one of the main important problems we have to care about. That's why you saw earlier that we have the feedback. The feedback system is going to pressurize the tank a little bit, and thus is going to help the rotary valve to push the material to be mixed with the air instead of allowing any percentage of the air to go as the rotary valve leakage. And also we have the QM, which is volume, the flow rate of the conveying air and the material. So you can see that wherever the tolerance is going to be high, we're always going to have an escape for the air to go up, generate higher pressure here, and this will obstacle the flow of the material. So just imagine if this material is going to be quite light, this gap here is actually going to be too large, and thus is going to sometimes stop the flow of the material totally to the system. So the leakage can be something between 10 to 50% of the supplied air. Also is going to be affecting the value for the high KL is going to reduce the value for the massive flow rate, and thus is going to be very important to determine the value for the air leakage in the system. Another way to overcome this problem is to use the nozzle injector. So next time, if you're going to visit any pneumatic air conveying system and you see a similar device at the bottom of the hooper, just remember that this will be the nozzle injector. So the air is coming from here, the material coming from the other side. The two streams are going to be meeting together, and the air will start to carry the material and push it forward through the piping system. Now, once again, we need to have some caution not to have the air going back. So it's going to go through. So you can see for the nozzle injector, and instead of having the feeder and have the possibility of the air leak to the upward, we're going to push the air using the nozzle. Thus, we're going to have very high velocity, and then it's going to go through the venturi, and the only way to go is going to be straight forward. Because the air stream is going to be releasing at a later end, and thus we are going to have negative pressure here instead of the positive pressure, and this will pull the material instead of blowing it up. The other time, so the increased velocity is due to the nozzle pushes the material into the pipe and then through the pneumatic conveyor. Another example for the nozzle injector. Once again, the very high nozzle velocity focusing in one direction will only going to give one way to the air to go, which is going to be through the venturi and then through the piping system. Negative pressure is going to be generated on that side. Now, another way to do that is by using the blow tank. So, of using the feeders, the mechanical feeders, we can simply pressurize the tank. So instead of having the open top tank, we're going to have a closed top one, and it's going to be sealed, only opened when we try to fill it. So we're going to fill the tank, pressurize the very high pressure, open the lower outlet, and thus the material will going to be forced to go in one direction, which is going to be filling the conveying pipes. So the steps of the operation is going to be: first we have the empty tank, to fill with the material, okay, and then again to close the material inlet. Instead of that, we're going to open the air inlet. So it's going to pressurize the whole tank until we're going to have a certain level of the pressure. Of course, we have multiple gauges there. And then we're going to open the material outlet. So the high pressure will force the material to run through the outlet, filling the pipe, and then we're going to close and repeat the process. So this is an example of the blow tanks. We can have either the top discharge, or we can have the bottom discharge. So this will be the first one, the top discharge. We're filling the material from the top, okay, pressurize the, filling the material from the top, and until we're going to, then we're going to blow up the air, pressurize the material, the whole tank, and the material will start to flow up through the conveying line. The other one is going to be bottom discharge. We're going to blow the tank from the bottom. We're going to supply the material through the conveying pipes, and it's going to go to the conveying system. Okay, now that's what you are going to see in real life about the bottom discharge. You can see that the outlet is going to be at the bottom, or you can have the pipe coming here to the conveying system, and that's what we call it, the top discharge. Now, how to fill this tank? Can you see this opening from the top? So when I get to stop the whole process, I get to lock this valve and open the one at the top, and then I get to open the feeders, which are coming down from the cooper, fill the tank, and then pressurize once again and make the operation continue. Now, I don't want to stop the feeding. Some application can take the waiting until we're going to fill the tank with the material. And that's if we're going to use a single blow tank. So it's going to be one blow tank, or so we're going to feed the material as a batches. So what's happened that we're going to have the cycle overhead. The blow tank is going to be filling, initial pressurization, and by the end of the cycle, we're going to have the Bergen, filtering, and the valve actuations. The average blow tank discharge rate is going to be something between 50 to 100% more required than the system capacity. So, for example, if the system is going to require, for example, 100 kilogram, are going to have the tank discharge rate should be more by almost 100%. Now, that's what happened in the single batch or the blow tank discharge. We're going to have the tank to be filled with the material from the inlet, close the inlet, pressurize the air, okay, until we're going to have a higher pressure, and this will cause the material to run through the pipelines. We can also have the parallel blow tanks. Now, for the continuous feeding of the system, I can have two parallel tanks. I'm going to use the first one. When it's going to be finishing, I will close this gate and opening the other. So this one will start to empty while this one is actually filling. And I think I have one of the video I selected earlier can show us the parallel system. I think this one. Yeah. Yeah, this one have the double tank. So you can see that's what we'll have in dual tank, and this will help me to have a continuous feeding for the pneumatic system. Two parallel tanks. So we're feeding one while emptying the other. So what you can see here that the feeding pipe or the conveying pipe is always going to be filled with the material. You're not going to have any interruption, and thus the feeding for this operation is going to be constant. Okay, so the other application is going to be the piggyback, or what we call the series type. Now, what we're doing here is that we're going to have intermediate pipe. This tank is going to be connected to the silo or the hooper. It's going to be filled. This one is pressurized and feeding the operation. Now, as this one is going to be emptying, we are going to stop that feeding. We stop the pressure. This one is filled and pressurized. Then, as we open the gate in between them, the blow up will be happen, and we fill this tank immediately. Close this one and start to refill this one once again, and then continue the pressure. Now, the most important application for the piggyback type is that we are going to have constant pressure inside this cylinder, because it's always going to be an equal pressure between the two types or the two tanks. Now, all these systems must have some bends and derivatives. So we're all not always going to have straight lines. There's no application where the pipe is always going to be straight. Always using the bend, we always try to prevent using the elbow, because you know that. Sorry. I'm using filter, but you can still hear the motorcycle. Sorry for that. Well, I don't know what to do with these things. I hope that you're not going to hear it anymore. Okay, so once again, we do have the bends here, and we not using the elbows, because the elbow is going to be very acute angle, and this will cause the turbulences to be happen. So actually, I know this is for gases, but I just want to show you things. So the selection of the bends and this will depend on the layout of your design, the types of the materials you are going to use, and types of the pipes you are using, delta P, pressure difference between the inlet and the outlet, the wear resistance, the product you are transporting, the application, the flow mode, and we may have some triangles that not mentioned here. So we need to know what do we mean by the types of the modes. The best and the lighter one is going to be the dilute phase, or we call the suspension phase. In this case, the density of the air, the mixture or the specific gravity of the material we are transporting is going to be very low, because the small particles are floating within the air. Now, the problem with this process is it's going to be good for the powders, but the problem is that it's going to be consuming a lot of energy for transporting less amount of material. We can have what we call the dense phase. Now, all these types are going to be considered as a dense phase. This can be either the single slug conveying, so the material will move in the pipe as patches, We can have the fluidized dense phase. We can have the internal bypass. We can have the low velocity slug flow, the external bypass by sending the pressure inside the pipe by using multiple outlets. We can have the low velocity plug flow, and we have the extrusion flow. Now, the extrusion flow is going to give you the best efficiency for the system. More material fed continuously through the piping system, but the problem again to have too much friction between the material and the pipe walls, and this will cause the wear rate of the piping system. So I think, yeah. So as you can see, different types have it in the patches. And in this pipe, certainly we'll get to have continuous flow to be happen. Different types. I don't think this RDGF thing. So this will be almost zero type because you can see that the particles are floating with more air density. Not sure if this one is a video, but yeah. So this is experimental work. Show different bands, different pipes, and different flow system or flow modes. So you can see that the material here is flowing as a dilute system. Yep. This is dilute phase. It's using high velocity air and low material feed. I think the next step is he's going to change that by increasing the material and reducing the flow rate velocity. Yep. So they slow down the air velocity, and then you will see that the material will be pushed as a patches. So what's happening here that the material will start to accumulate at the bottom of the feeder, and then it's going to be accumulated and pushed in one patch, and that's what we are going to achieve. Okay. That's rotary valve application. I'm just looking for again to have the more dense phase than this one. I think that's solved that, yeah. Okay, so the first one was low pressure, high pressure, and low velocity, and high velocity. The other one was low pressure and low velocity. So after we're going to reach the final destination of the conveying, which is going to be the accumulating tank, we need to have the material discharging methods. And this can be either the cyclone type, where the material starts to hit the walls in its rotation, and the heavy material will be accumulated at the bottom, while the air is going to go at the end. So what we have in the cyclone is the inlet is going to be in this direction, start to rotate through the cyclone shape and then the funnel. And here we're going to have an escape for the air to go to the outlets. The other way we can do is using the fabric filter. Okay, and the fabric filter is going to allow the air to escape, but the heavy material is going to be accumulated at the bottom. So this will be the cyclone separator as we mentioned earlier, and this one is going to be directly into the process vessel. And doing that, Okay, and of course we should have certain filter to let the air escape, and we can have the filter receiver. Now, this will be a parallel outlet. Now, why are we doing this operation? Because we are going to fill the tank number 1. Tank number 2 is going to be full. Tank number 3 is filling while we emptying the tank number 1. So we're going to have one of the tanks is going to be full. Okay, so why are we doing this operation? Because we would like always to have a positive pressure inside the system. We don't want to have the pressure to be escaped continuously. So we close this valve while the other 2 tanks are filling. When we'd like to empty this one, we're going to close the valve and close the valve and then empty the material. So this will be an operating pressure. We're going to have the plant layout for the multi-destination points outlet as point number 1, 2, and 3. Usually, the total pressure in total is going to be the pressure at the input minus the pressure at the exit. Now, this will be the case for the twin system or the parallel system. We're going to have the feed or the supply pins. And in that case, we're going to have a negative pressure to be generated in the system because we're going to have the prime mover at the end of the system. Now, in that case, the delta PT or the delta of the pressure total is going to be the input pressure minus the exit pressure. Okay, so let's find the option. Now, that's what we call the ferry hair. One of the main problems we have in the component is the wear. So, due to the effects of the ferry hair, we start to have this fall. Of course, the material will start to accumulate here. It's not going to be a bigger problem when dealing with this safe material. But just imagine that this material is going to be something like a chemical agent or, for example, hazardous thing like it can explode. So actually, this leak can be very dangerous for the workers. And of course, we're going to have loss in pressure continuously. I'm sorry, it's the angel. Yeah. So the angel hair formation is going to be happening because of the falling pressure. When I get to have a bend, long brainless elbow, the materials start to move along the wall, and at the end is going to release it as the angel hair format. This will cause a very high friction at that point, and this will cause the friction is going to be too high until it's going to wear the material. So how we can eliminate the angel hair? We can usually this example for the plastic resin moving through the elbow and hit and slide along the inner wall of the elbow, creating both an impact zone and sliding zone or a friction zone. So to overcome this problem, we can simply have the cutaway tubing, which is going to be a riffled or spiral grooved elbows, which cause the resin pellets to tumble out through the elbow instead of slide along its wall. We're going to have it like this way. It start to rotate and leave instead of creating the angel hairs. Another process to do that is simply having the extension. Now, the main problem we have here that this extension, yes, is going to prevent the angel hair creation, but it's going to run slower, run cooler, and then we need to remove it. And the problem we're going to have here is we're going to lose some energy required to move the material. Now, the minimum conveying velocities in the pressure and vacuum system, or what we call dilute phase, is going to be as following. For the alumina, the bulk density known for this material as the average value is 800 kilogram per cubic meter. The velocity pressure for this system required is going to be 19.8 meter per second. And in the case we're going to use the vacuum system that pulling the material, the velocity is going to be 33.5. Now, this was powder. If we're going to go to the beans shape, like the coffee beans, that's the 670. The velocity is going to be reduced to 13.7 in the case of the pressurized system. And for the vacuum system, it's going to be reduced to 22.9. So you can see, actually, if you're going to follow this table, that the higher density material requires a higher velocity pressure for the conveying. Because simply is going to be heavier, and thus we need to add more velocity to make things move. Now we are going to have a relationship between the wear rate against the velocity. Definitely higher velocity. Okay, this will be the mass of the sand conveyed, and this will be the area of velocity. We're also going to use the m value to be something between 2 to 6. Typically, we are going to use 3. A high velocity will going to increase the wear rate. Higher wear rate for the final system, as we're going to run the system at higher velocity. So that's why we always get to prevent using the Dennis system as continuous one, because the material will get to run continuously, moving more material. We're going to have more contact with the wall, and thus the wear is going to be happening much faster. Now, some of the characteristics we have for pneumatic conveying system is going to be discussed in the following slides. So the PCC will simply going to define the conveying performance of the given products and the pipeline. It's going to be effective for the troubleshooting, designing, and optimizing, operating, and the debottlenecking of the conveying system. The PCC is going to have 3 main parameters plots. First one is going to be the MF, the other one is going to be the MS, and the third one is going to be the delta PT. Now we learned about the MS. The PT is going to be the total pressure difference between the input and the output, and let's see what will be the MF value. So the MF is the conveying air mass flow rate in kilogram per second. The MS is the solid mass flow rate in kilogram per second or ton per hour. Delta PT is the total conveying pipeline pressure drop in kilopascal. So this is an example for the ash. The diameter of the material is going to be about 52 millimeters. The length of the pipe, the diameter of the pipe is 52 millimeters. The length of the piping system is 71 meters, and the MB is going to be equal to 10. So if I get to sketch the conveying air mass flow rate in kilogram per second against the total pipeline pressure drop in kilopascal for the 3 different flow rates, or the MS value, okay. So this is the 0 value, where almost going to have no pressure drop. It's going to be very small. As I'm going to use higher flow rates, because I'm using higher velocity in that case, you can see that for the velocity of the air we're going to apply, the Dennis rate is going to be anything between the 4 and the 5. This area is going to be the blockage. The material is not moving. I need to increase the velocity, and I'm going to have the Dennis. If I'm going to increase the velocity further, I'm going to have the dilute phase. So anything, let's say between 4 and 5 is going to be Dennis. Less than 5 is going to be non-moving. Above 5 is going to be the dilute phase. Higher flow rate for the material we have, higher velocity for the air we're moving, we're going to have more dilute phase conveying. So in the case of the conventional piping system, this will be the air massive flow rate, and this will be total pipeline pressure drop. The RTL is going to be here, which is going to be the rated tolerances line. After that, we start to have the Dennis and the PMC. After the PMC, we start to have the DDU type. Now, in the case of the, that will be the case of the powder. In the case of the granules, anything at low velocity is going to be unstable or blockage. The solid massive flow rate will start to begin at higher velocity. We're going to have the dense smooth. We're going to have again where the material is not going to be stable. So it's going to be running as a mix between the dense and the dilute. So it's going to be sent in small patches of the material. And the higher velocity, we're going to have the deposition, then we're going to have the dilute rate after the PMC line, which is the pressure minimum curve. The RTL, of course, is going to be the reliable transport limit. In the case of the gravity of the coarse material, we're always going to have the blockage until we're going to have the reliable transport limit, where the velocity is going to be high enough to remove the material, and we're always going to have them as a dilute. Now, simply we're going to have dilutes, we're not going to have them as zenith because it's coarse material, it's quite big. So we're always going to have cavities in between them. So I just put the powders, the granules, and the coarse in a separate pages. Now, some important equation we have for the pneumatic conveying. The first one for what we call the continuity equation. The continuity equation said that the velocity, the mass flow rate of the air is always going to be constant at any point within the system. So the density of the air, for example, at the entrance, multiplied by the velocity of the air in the entrance, multiplied by the cross-sectional area of the pipe, is going to be the same at any point through the pipe. Just remember, this will be the main key we're going to use to find any unknown in our design procedure. The second important equation we have is what we call the steady state conveying. So we said that the MF is going to be the continuity equation. So the MF in that case is going to be constant, which is going to be the density at the entrance multiplied by the velocity at the entrance multiplied by the cross-sectional area at the entrance. It's going to be equal to the density at the end multiplied by the velocity at the end multiplied by the cross-sectional area at the end. So whatever will be changed, we're always going to have a constant value for the MF. Now also we can use the ideal gas law, or the density of the air is going to be equal to the pressure divided by the RT. Of course, you know that the R is the gas constant and the T is the temperature in Kelvin. The PF is going to be the pressure plus the atmospheric pressure. The M star is going to be equal to the MS divided by the MF. Delta PT is going to be equal to the final pressure difference plus the steady pressure, the PS. The delta PF is going to be equal to the lambda F multiplied by the rho multiplied by the velocity squared divided by 2 multiplied by the length of the pipe divided by its diameter. The value for the lambda F we can get from the Moody graph that we learned how to use it in the fluid dynamics. Delta PS is going to be equal to the function of lambda S, the M star, and other parameters, and this can be only found through research. You remember that Moody graph we're going to use a lot in the next two design procedures for the pneumatic and for the liquid. So in the Moody graph, what we need to find is two parameters, and then we can find the other parameters. The usual parameters we can find are going to be the round number, because we can calculate that, and also the type of the pipe and its relative roughness. Of course, the mu is going to be the surface roughness of the pipe from the inside. The diameter is known, so we can calculate the relative roughness. Round number can be calculated as long as we know what will be the value for the diameter, the velocity, and the viscosity. By finding these two values, we make the intersection, and thus we will be able to find the friction factor F. And from there, we can continue to find the other parameters in our design procedure. So you can see here that we don't have to calculate anything. We can simply using the standard value or the approximate value. So most of the pipes we are using is going to be either the cast iron or the galvanized iron. In more advanced calculation, we can, advanced system, we can use the riveted steel. So for example, for the galvanized iron, the value for the mu is going to be equal to 0.0005 millimeters. So we can use this value, okay, the 0.005, which is going to be a line between these two lines. And for example, that final number is going to be equal to 4 multiplied by 10 up to the power 6, which is going to be here. We intersect the two lines, and then we're going to intersect to find the value for the friction factor, or lambda. Okay, so we found the mu over d first. We find the round number second. We choose one of the lines, like the here we're choosing the 0.001 as an example. Sketch a vertical line from the round number of 3 million. It's going to have the intersection here. Make the horizontal line, and we can find the value for the friction factor F, or what we call as a lambda F. Now, I think that we only have this example before we are going to close the session. I prefer that we take a break because we already had 1 hour session. And then we are going to start discussion about the assignment before we're going to go for this example. So I'm going to stop that recording, and we're going to come